Thank, Many thanks to the organizers for this opportunity to speak at this meeting, and I very much regret not being there, especially since it appears there are generous coffee breaks and meal breaks. But teaching has resumed, and so it's difficult for me to travel this period of the year. So I actually slightly changed the content of my presentation, but it's mostly what I announced. I first start with, it will not be on foundations of quantum mechanics. It will be mostly on deformed symmetries and observations. But let me start, after following some of the other presentations, as someone who has lived long enough somewhere at the boundary between relativity and quantum physics, I must signal a certain discomfort I've had for a long time, where when one thinks deeply of relativistic issues, the notion of observer is highly schematized and perhaps too much. And then when I hear colleagues thinking about quantum foundations, the idea of observer is totally not schematized. Is a full-grown human, and actually I feel we are not ready for that, but I also think we must be ready to go a bit beyond the ultra-schematized description of relativistic experts. So this is meant only to be an invitation to see this community, to see if there is something interesting to be found by just gradually building up the description of an observer. And there will be something about observers, but not their nature. There is something about agency that I will get to during this presentation. My main dish, consistently with some of my research in the past, has to do with the role of deformed symmetries in quantum gravity research. In part, the first part will be still on kappa Poincaré very quickly. Kappa Poincaré is a scenario for deformed symmetries that myself and many others have been studying for several years. And I will just summarize again how this could be relevant to some of these underground experiments, although Antonino already did that even better than I can do for sure. And I'm guessing Michele Arzano later on in this meeting will do that also much better than I can do, but I will perhaps indulge more on the motivation for this kappa Poincaré toy model. And in the second part, I will have instead a new model, which just recently we are starting to understand, and that I am proposing to the community as a new avenue for perhaps finding experiments, hopefully Earth-based experiments that can test it. So let me start from reviewing the main motivation for the idea of deformed relativistic symmetries in quantum gravity, at least the way I see it. When I was a PhD student, there was already so many seminars where the Planck length was kind of unquestionably presented as the minimum allowed value for wavelengths. And it appeared nobody wondered about it, but I started to be concerned. How could we have a minimum wavelength fixed by the Planck length, considering that relativistic transformations contract wavelengths? So the minimum wavelength for one observer could not be the minimum, the same wavelength could not be the minimum wavelength for another observer as a result of Lorentz contraction. The logical order was that then, a few years later, some results started to appear in the quantum gravity literature, finding hints that the dispersion relation could be modified in ways that John Ellis very nicely described this morning. And the first interpretation of these results was that, well, then perhaps these quantum gravity models are models with the preferred frame, because if you go beyond our present relativistic description of nature, one possibility, of course, which we cannot exclude for quantum gravity, and again, John this morning very fairly described the motivation for this, we might well have a preferred frame, so a total breakdown of relativistic invariance. What I became fascinated with in those years was the hypothesis that perhaps we should not, or at least we should not necessarily, maybe that's what, maybe nature wants to break completely relativistic invariance, but I started to fancy the idea that this notion of minimum wavelength, or the notion of a deformed dispersion relation, and all similar results, non-standardly relativistic results which were arising in the quantum gravity literature, might be accommodated in a picture which is still relativistic. And after a bit of trial and error, it was figured out that such pictures do exist. And some of them do not involve quantum groups, which is where I would focus today, following a bit what Antonino did this morning. But there are plenty. There are plenty of scenarios when you can have new relativistic laws, and but still preserving a fully relativistic description, with actually the new element that these relativistic theories have not one but two special relativistic scales. In addition to the speed of light scale, you naturally would have in these pictures, with the similar role of invariant of the theory, the Planck length. The quantum group, the role of quantum groups in this literature, which I stress, there are alternatives. You can have this doubly special relativity, DSR theories, with other types of mathematics, but the most studied, evidently because it gave fruitful results, is based on the notion of a quantum group. Quantum group symmetry, which often means non-commutative space-time description. And already this morning, Antonino mentioned the kappa Poincaré, kappa Minkowski framework. For me, it's important to stress here that this space-time, kappa Minkowski, is evidently, especially for the second part of my talk, it's important, is evidently invariant under classical rotations. There is nothing in the defining commutation relation of kappa Minkowski that would affect classical rotations, classical space rotations, but boost and translations are affected clearly. So much so that one might imagine that the symmetries are broken. Translation and boost symmetry might be broken at first sight. For example, classical translations are not a symmetry, evidently, of these commutators, as shown. I don't know if you can see my pointer when I move it on the screen. Can you now see that I'm circling one equation?
We do, Giovanni.
Thank you. So you see easily that this, under a classical notion of translation, the commutation relation of kappa Minkowski are not invariant. However, well, translating in the classical sense, which is adding a number to the coordinate when the coordinates are non-commutative, is actually somewhat naive, evidently. And it has been figured out that actually this space-time has a rather good translational invariance in terms of a differential calculus, which also was mentioned by Antonino, with non-trivial, correspondingly non-trivial properties. So we have translation invariance. We actually also have a which is deformed because it's implemented via this non-trivial differential calculus. We also have deformed boosts on which I will not focus, but they are the reason why the dispersion relation is modified in this picture. What I will just dedicate one slide on is the fact that as a result of this novel property of translations in this space-time, when you try to introduce a translation generator, capital P, in this picture, and here I show what is the typical definition of a translation generator in Kappa-Minkowski. You prescribe the action of this generator on ordered exponential, not on whichever plane wave. Plane waves in a non-commutative space-time must follow some ordering prescription. The hope is that the end result, and typically this is what is found, is independent of the ordering, but you must fix an ordering, because since x and t don't commute, for example, in Kappa-Minkowski, that is otherwise ambiguous. You define the action of translation generators in this way, but then these generators have a surprising property for a physicist, a property well known to mathematicians who have been playing for decades with quantum groups, but surprising for physicists, because as a result of the fact that evidently the product of plane waves has an anomalous property. In the case of Kappa-Minkowski, it produces these exponentials here and there. Then the action of the generator of translations on product of fields, here I have a product of plane waves, as what is called the non-primitive coproduct. So the Leibniz rule is violated in a consistent way. There is a consistent quantum group structure behind all this, but it is, for a physicist, rather striking, for a standard physicist, to see the Leibniz rule does not apply to these generators. And there is, for example, in this case, this exponential factor that corrects the Leibniz rule. This is the key ingredient that leads to a rich description in Kappa-Minkowski of that idea which I mentioned before of the formation of relativistic symmetries. And the part which I did not describe, the modification of boosts, is the part that produces a rich phenomenology in astrophysics, which is pretty much the one that was described by John Ellis this morning. John had in mind a scenario where relativistic symmetries are actually broken, but some of the phenomenology he described, as many of you already know, is also applicable to this deformed symmetry scenario. The two key applications that John mentioned, the one about travel times of signals, so dispersion in vacuum, that is an effect that you can describe, as far as we know, equally well in a broken symmetry picture and in a deformed symmetry picture. John also described these, what I call anomalous thresholds. Some particle physics processes like gamma gamma to E plus E minus can be, of course, affected if you touch standard relativistic invariance. It turns out that if you break relativistic invariance, these processes are affected very strongly, whereas if you deform relativistic invariance, that does not happen. So it's a similar phenomenology to the one of breakdown of relativistic invariance, but with the difference that you do not have striking predictions for particle reactions. The thresholds for particle reactions remain pretty much unaffected as a result of the fact that you are doing something smoother than breaking relativistic symmetry. You're just deforming them in a smooth way, and some things are robust enough that they don't get affected. And this is the main difference between the two scenarios. I will just it was implied and mentioned in Antonino's talk, and it will be discussed, I'm guessing, much better in Michele's talk. But let me remind once again why this issue of the modified Leibniz rule, what we call, what literature calls non-primitive coproduct, this lends itself to the interpretation of a modified sum of momenta. If you think of, in particular here on top, this product of plane waves, the way it works out, it suggests that momenta are being added in a deformed way. And this is the main reason why we suspect that these constructions should have a role also in things like Pauli exclusion principle and all issues that have to do with symmetrization and anti-symmetrization of states. Because, you know, if we, you know, assuming that we can read the total momentum notion from the coproduct, which is something which is still debated and debatable in the literature, we are missing the crucial ingredient of a Nether theorem adapted to these new symmetries. For interacting theories with these new symmetries, we are unable to produce the equivalent of a Nether theorem. So we don't really know what are the charges associated to these generators. But we can reasonably guess that this non-primitive coproduct property of the generators will translate, as I mentioned, into, and as Antonino implied, into a modified law of composition of momenta. And then evidently, you cannot symmetrize and anti-symmetrize states naively, because otherwise you would not have states which are eigenstates of momentum. And this has led to a number of proposals. Antonino Marciano and Michele Arzano have been among the most influential, but a large community has been attempting to handle this challenge of symmetrization and anti-symmetrization of states in Kappa-Minkowski and Kappa-Poincaré framework. I will leave it at that, assuming that already, well, knowing that Antonino already said much about it, and assuming that Michele will say more, even more. But let me stress again something connected to the question raised to Antonino. We cannot be sure that this property of the generators, this non-primitive coproduct for the generators, actually translates into a corresponding property for the charge which are conserved when these generators describe symmetries of my theory, because we don't have another theorem for this type of symmetries. And so while it makes perfect sense to assume that the connection would be strong, we are there waiting to understand how to really combine momenta. And this would be a major breakthrough that every time I meet Catalina and Antonino, I promise is forthcoming, but this is for 10 years now. It's very hard, but really addressing this challenge of understanding what are the properties of the charges which are conserved when such, let's say, funny generators are a symmetry, describe symmetries of the theory, is a major challenge theoretically and could be an important asset then for phenomenology, since it enters in particular in this Pauli exclusion principle and other symmetry, anti-symmetry related properties of the theory. This to summarize, first part was to summarize things which are already well known or known to some extent for a few years. Let me go to another, instead, very recent result. We are actually finishing up the paper, hopefully this week. Because you see, I was feeling the need to Kappa-Poincaré, as I did not take time to explain why, but it's really a wonderful model, most likely a toy model, but surely a wonderful toy model for exploring modifications of symmetries in quantum gravity, which leave space rotations unaffected, and only translations and boosts carry a trace of that. That makes a lot of sense. It's comfortable for many applications. So I am perfectly fine defending that was a good place to start. However, it's now really nearly 20 years that a good part of the quantum gravity literature is devoted to this kind of scenario. And I think maybe we should also go back to the assumption that space rotations are left unaffected at the quantum gravity level. And this is what inspired, in part, a recent project which involves quite a few people, 3 PhD students in my group, Vittorio D'Esposito, Giuseppe Fabiano, Domenico Frattulillo, and 2 more senior researchers, Philip Hearn and Flavio Mercati. And what we focused on is, well, let's take the possibly simplest scenario for deforming rotations, and let's try to understand what would be the implication if that was the whole story. Then you can imagine this being inserted into a wider realm of deformation of symmetry. But then we wanted to focus on this SUQ2 quantum group, which is a candidate for describing a deformed notion of space rotations. And as usual for my research, the literature on it, it's amazing what we discovered in this project. The most amazing thing, SUQ2 is the most studied quantum group. There are lots of mathematical results, but some very basic questions for nearly 30 years, SUQ2, maybe 35 years, has been studied intensely by mathematicians, but also mathematical physicists. And there are so many mathematical results, and still we discovered that some basic questions of interest for physics had not been addressed, which also shows you how the literature is fragmenting in kind of a spectacularly awful way. So we went to square one, and we, in some sense, investigated the idea that this quantum group SUQ2 describes space rotations. We took, of course, as starting point the classical SU2 and the way it can describe space rotations. In some sense, SU2, the classical SU2 describes space rotation via its connection to SO3. And so I have here, just as a reminder, a standard parameterization of the SU2 classical group and the relation between the parameters of this description of the classical SU2 with the Euler angles that we care about really when we do physics of rotations, or at least they are one way to express what we care about when we're talking about rotation transformations. Here on top, I summarize the basic connection between SU2 and SO3, which is a canonical homomorphism, which explains why it was comfortable for us to work with SUQ2, but we are, in some sense, hoping to assume that what we find is relevant for space rotations. How do we get from SU2 to SUQ2? What is the deformation that leads to the quantum group structure? It's this Q parameter, which, for example, now you see in some of the formulas that define SUQ2 here below. Notice, for example, that A and C, which at the classical level would evidently commute, they have commutation rules which involve Q, the deformation parameter. This deformation parameter is somewhat to be carefully treated with respect to the parameters eta, for example, that Antonino had this morning for another picture, the theta canonical picture. Usually the parameters that are introduced to be, it's a deformation when they are small. But you will notice in this formula that in the Q deformation, the deformation is small when Q is close to 1. So what we have in mind is that Q differs from 1 by a very little amount. As you also see in the defining property, if Q is equal to 1, you get back the original picture, not Q equal to 0. Q equal to 0 is a disaster. This is just a convention, but it's important to know this, otherwise there is a change of tone concerning the smallness of the deformation. This is still a very small deformation. The fact that it's small, you will notice in some formulas by seeing that when Q is close to 1, things fade away. The most important contribution that we give in this paper is that simply we took as an ansatz, which actually, however, survives a number of consistency tests. We took as an ansatz that the relationship between Euler angles and the parameters of SU2, which one has at the classical level, we found no obstruction to preserving this connection between Euler angles and parameters of SUQ2. So this gave us, for the first time after large, fully mathematical literature, for the first time a handle on grasping what would be the implications of having SU2Q governing symmetry transformations. Among the results, we have immediately the fact that there is one axis. So the key idea that I want to convey, which is difficult to grasp in a few minutes, but I will just flash it a couple of times and then maybe it will require some metabolization by those who are interested. What we found about SU2Q, which is not clear, it's a group of transformation under space rotation. It's a symmetry. It's a tool suitable for describing a quantum, but rotation invariance. However, there is, in some sense, the emergence of a preferred direction in a way that is, however, agency dependent. It's not a preferred direction in the universe. It's not a breakdown of rotational invariance. It's a remarkable notion of rotation symmetry, such that actually each observer in its own reference frame will have a preferred direction, but that direction is not preferred for other observers. Alice and Bob will have two different preferred directions, and there is a perfectly good rotation matrix, of course a quantum matrix, connecting the description of the two observers, which can be perfectly nice rotation symmetry of a theory. So it's kind of a novel way of having some sort of anisotropy in the description of the universe by one observer, even though the universe is isotropic. This all might sound crazy, but when the paper will be out later this week, my only challenge today is to make you intrigued by it. But then when the paper will be out, I think all this will be more digestible. So the first result, which has to do with this anisotropy, is that there is only one axis around which you can have sharp rotations. Each observer can, in some sense, choose this axis at its own will. It's the first axis in the construction of its reference frame. And rotations around this axis can be sharp, and they are discretized, following a rather funny formula, which involves the arc sinus of this Q deformation parameter to power n. So yes, you see that the spectrum is not equally spaced, is more dense at large n, where actually theta gets small, and instead it becomes quite tangibly discretized at larger values of theta. And these, I guess, the first time that such a picture of discretization of rotations. These are not discrete rotations. These are quantum rotations, but they have eigenstates. So you can have, in general, even rotations around the special axis will be fuzzy, but you have the possibility of specific rotations which are sharp, only, however, for certain values of the rotation angle. What is the interpretation that we give of this quantum description of rotations? Which is what these I explained a particular case where we have eigenstates, but in general, all rotations in this SU-Q2 picture will be fuzzy. And how these fuzzy rotations describe what is the physical interpretation of these fuzzy quantum rotations connecting two different observers, Alice and Bob? Well, these operators act on some Hilbert space, of course. These, the elements of these SU-Q2 representations are themselves operated on some Hilbert space. We interpret this Hilbert space as the representative of the relative orientation between the two reference frames. So the rotation from Alice to Bob is the action of a certain operator on a state in the Hilbert space, which represents what is the transformation between Alice and Bob. So the nature of the relationship between Alice and Bob is a state in a Hilbert space. And then by interrogating with this state with our operators, we can understand in physical sense which sort of rotation. In some cases, it could be a quasi-classical rotation, if it's not too fuzzy. We understand which sort of rotation connects Alice and Bob by interrogating the state connecting Alice and Bob in this Hilbert space, which of course is not the Hilbert space of quantum mechanics. This is an auxiliary Hilbert space that just codes the information about the possible relationship between two observers with respect to SU-Q2 described rotations. And so, as usual, then once you have this interpretation, clearly, the attempt to have a quasi-classical rotation means to estimate the rotation matrix on this state that describes the connection between A and B. That expectation in the state of the matrix will be, the class, would give the first intuition of what at the classical level that rotation would be. But then due to the non-commutativity of everything which is in this picture, we will have non-vanishing variants of this matrix element of the matrix R, which rotates Alice into Bob. So the rotations between Alice and Bob are clearly fuzzy, and you can have some sort of quasi-classical rotation by attempting to minimize these delta ij, but actually we have results showing that this delta ij cannot be minimized at will in general. It can only be minimized in that one special direction, which I mentioned on the previous slide, what you could choose, for example, as your z-axis. Pure rotations around the z-axis, there are some which are sharp, and these are the eigenvalues that are shown in the figure. But any rotation which involves other axes in addition to the z direction will be inevitably fuzzy. What are the implications for phenomenology is still unclear to me, but it seems pretty pervasive potentially. what some of the things about interpretation that we are starting to figure out is, for example, if one observer is looking straight, so aligns its z-axis toward a certain object, could be a star, could be a distant star. This axis, if he aligns the z-axis in the exact, if he has, aligning is difficult because it cannot be sharp. But if the observer happens to have his z-axis aligned to the direction where he is looking at the star, or she is looking at the star, then there will be no additional fuzziness due to quantum properties of space-time in the way the observer sees the star. But that same star, if another observer is looking at it with the z-axis not aligned, of course, to the direction of the star, then the star will produce fuzziness for that observer. So instead of seeing a sharp point in the sky for an ideally narrow star, the second observer would see a blob, a fuzzy picture. And again, this is totally new with respect to other pictures of quantum space-time, where you have fuzziness in many of these pictures, but the fuzziness either is there or is not there. If you are at in the right regime, the stars will all look fuzzy to all observers. Instead, here there is a dependence on the choice of the axis made by the observer, which is scary, but extremely fascinating from a conceptual viewpoint. And this is where this notion of agency, which we are somehow pushing for this new model, in some sense, how the observer sees the universe, what space-time it perceives, it depends on the choices made by the observer in setting up his or her reference frame. In particular, the choice of this z-axis, as traditional, we chose z as the letter of the special axis. The choice of z-axis really changes how the observer sees the world. Okay, it's not possible to it's not possible to correct. It's not just a misleading inference that you could correct by it, by knowing, okay, I'm not using the right direction, so what I'm seeing, there is no way to cancel the effect. There is no true universe. There is no true space-time for the observer, because if the observer chooses a certain z-axis and he wants to choose another one, the rotation between the two is fuzzy. So he can never recover fully how the universe would look if he or she had chosen another z-axis. All this is, I realize, is shocking at first, but it's not the first time that I get intrigued by something a little novel, and I hope it will give rich phenomenology as other times when I got fall in love with such crazy ideas. But still, on the technical side, this paper that we are basically ready to announce represent surprisingly remarkable progress in a field which has been heavily studied for 30 years, with a large literature on all sorts of mathematical properties of the SUQ2 group. And to our knowledge, not even one paper describing how this new quantum group would affect the rotations that connect two observer Alice and Bob, if those rotations were described by this quantum group. So on the technical side, we are pretty proud of what we accomplished. On the interpretational side, we are totally in love with these crazy things that we are finding, but certainly we cannot at present assure you that this will all make sense in the end. But if it does make sense, it's one of the reasons why I pointed at this meeting, If it does make sense, it appears clear that it will be relevant for phenomenology, and potentially it's more likely than other quantum gravity ideas to show up in Earth laboratory, because when you deform boosts, there is it's long to explain, but there is a certain tendency then for the deformation to depend on the ratio between, say, the wavelength of the particle and the wavelength and the length scale which has deformed the boost, the inverse of this ratio, which is very small in a quantum gravity picture. When you deform rotation, actually, there is no, the only small thing you're fighting with is Q. But as far as we can see, there is no role played by the energy of the particle. For in-backward dispersion, for example, the effect is very tiny unless you go to the highest energy particles that the universe shoots at us. Here, because this is boosts, it's a dimensionful notion, and it's obvious that then the effect will depend on dimensionful quantities like the energy or wavelength, if you want, of the particle. But rotations are a dimensionless motion, and we don't see anything other than Q, this dimensionless quantity, to play a role in the smallness of the effect. It's clear that Q will be very small. Quantum gravity will set it. We also have some estimates in some quantum gravity models where SU-Q2 arises. Basically, Q is obtained combining the smallness and the Planck length and the smallness of the cosmological constant. So it's a really small number, but it's a number. It's not, there is no further suppression, or at least if, let me put this way, there is no disadvantage testing this on Earth with respect to testing it astrophysically, because the effect is not amplified by energy of the particles, and as far as I can see so far, not even by the distance traveled by the particle. So it's perhaps too early to imagine dedicated Earth experiments or developing a phenomenology, but the hopes can be high. And on this, I stop.